All right, hello everyone. Welcome to my channel. I'm Thomas and I do videos on educational topics. Today is video number 189 on the reciprocal system of theory from Dewey B. Larson. And Mr. Larson's theory is called the reciprocal system because there is a reciprocal relationship between space and time. In Larson's system, the universe is made out of motion. Not matter, not energy, but motion. And motion is the relationship between space and time. So we have a universe composed of motion. Space and time are the constituents of that motion. So normally we recognize space and time as kind of being like the container of the universe. The universe is occurring in space or time. But in Larson's system, space and time are actually the contents of the universe. And they have a reciprocal relationship. So motion is the constituent of the universe, and motion is a fraction where time or space is the numerator and space or time is the denominator. It is a bit more complicated because space and time can be multi-dimensional, 3 or more dimensions. Larson calls this coordinate space, which we recognize XYZ coordinates, and also coordinate time, and which we don't generally recognize, and which has gotten me kicked out of a physicist's office for even suggesting it. And then there is also the scalar aspect. A scalar motion is a motion that has a magnitude, but it has no direction, which you can envision by taking a balloon, putting dots on the balloon with a magic marker, and blowing up the balloon. All of the dots are moving away from each other, but in no particular direction. And that is what Larson calls clock time, the progression of time. Time is always getting later and later and later. But since the reciprocals have the same qualities, there is also what you call clock space. Space is always getting farther and farther and farther apart. And that is the progression of space. Now, there is one more thing that space and time have in common, and that is the discrete unit postulate. Both time and space come in discrete units. They are not continuous. There is a minimum chunk of space and time. Even though those chunks are very, very small, they exist. So there's not a continuity, but there is a discreteness about space and time. And exactly 1 unit of space in 1 unit of time, space over time, which is speed. The car is moving 20 miles per hour, 20 miles of space in 1 hour of time. But 1 unit of space in 1 unit of time is the speed of light. And so that is really looking at really the origin of the universe, or the midpoint, or the null point, or the what Larson calls the natural reference system, or even the ether of this universe is the speed of light, moving outward in all directions, scalarly. And that there is half of the universe that's moving slower than the speed of light, which we recognize as the material sector. And this is where we make all our observations and measurements. And this is where we have our 3-dimensional space, coordinate space, accompanied by 1-dimensional scalar time, the progression of time. 3 dimensions of space, 1 dimension of time in the material sector. But in addition to that, there is also a half of the universe that's moving faster than the speed of light. Larson calls this the cosmic sector. And in the cosmic sector, we have 3-dimensional time. 3-dimensional time and 1-dimensional scalar space, or clock space. So we have coordinate time and clock space. Space is always getting farther and farther and farther apart. You could also think of this as with the material sector as the universe of matter, and the cosmic sector as the universe of antimatter, which isn't exactly a reciprocal, that's more of a negative, but it's just with the terminology, antimatter maybe isn't the right term, but it's the one that the scientists use. So this would be what the scientists would term it as. Maybe Larson would call it. Larson did call it cosmic matter, but he's referring to what the scientists call antimatter. Okay, now what Larson did is he basically derived those relationships, and then he created a theoretical universe through a process of deduction. So, okay, this is what we know is true. If this is true, then this is also true. And then if that's true, then this is also true. And so it's a chain of deduction where he derives the general, mechanics and physics of the universe. And I went over that in about 15 videos earlier in the series. It was going over a paper that Larson gave called The Outline of the Deductive Development of the Reciprocal System. So you might want to go back and look at the universe that he deduces point by point, and then he makes identifications. The things that come out of his universe, he tries to figure out what those things are in the scientist universe, if anything. Okay, now today we are looking at his 1979 book that is called Nothing But Motion, and this has to do with physics, atomic physics in particular. And we are on chapter 13, which is on physical constants. So these are constants like, Avogadro's number and other constants that have come up in science. Larson is pretty opposed to the whole notion. He thinks that the constants, they should all boil down to units of space and or units of time, multiplied to the first, second, third, or more dimensions. And he was just going over this concept of secondary mass, which is a pretty difficult concept, but we will start right there, beginning his explanation. Because of this directional freedom in the time region, now remember that the time region is the region inside a unit of space. Space and time are discrete. They only come in discrete units. And if your unit of space is this size, it would really be like a sphere. But if the unit of space is this size, there's no space less than that. Once you get less than that, you are in a realm of time. And Larson refers to that as the time region. And on the other side of the universe, in the cosmic sector, there's such a thing as the space region. There's always this reciprocal relationship. What goes on in the material sector, exactly the same thing is going on in the cosmic sector, except that you're reversing the roles of space and time. Okay, so because of this directional freedom in the time region, the secondary mass may be either positive or negative. Furthermore, the directions of the individual displacement units are independent of each other. And the net total secondary mass of a complex atom may be relatively small because of the presence of nearly equal numbers of positive and secondary mass components. Now remember that a direction in space is independent of a direction in time. So they are independent of each other, the directions of motions in space and motions in time. This directional variability introduces a number of complications into the secondary mass pattern of the elements. The complete pattern has not yet been identified, but a substantial amount of information is now available with respect to the values applying to subatomic particles and the elements of low atomic number. The magnitudes of the natural units applicable to physical quantities are independent of the sector or region of the universe in which the phenomena to which they relate are located. As explained in Chapter 12, however, only a fraction of any physical effect can be transmitted across a regional boundary, and the measured value beyond that boundary is substantially less than the original unit. That's what Larson called the interregional ratio. Remember, there's 4 separate regions of this universe, and in those 4 separate regions, when you cross the border or when you measure across a border, those the rules change across the borders, and when you measure across a border, you have to reduce the value. Because you're not, or you would really, in some cases, even increase the value because you're not seeing everything that's actually there. You're only seeing a fraction of what's there because it's a scalar motion, again, with this directional independence. And so you're only able to see one direction out of many. Okay. This is the principal reason for the great disparity between the magnitudes of the primary and secondary mass. A unit of mass in the region inside unit distance is inherently just as large as a unit of mass in the region outside unit distance. But when both are measured in terms of their effect in the outside region, the inside or secondary mass is reduced by the interregional ratio, which in general is approximately 1 to 150. For a full atom, it's 156.44, and for a subatom, it is 142.22, which he derived in the previous chapter, if you want to go back. In this chapter, we are dealing with some very small quantities, and for greater accuracy, we will extend the previously calculated value of the interregional ratio to 2 more decimal places, making it 156.4444. The reciprocal of this ratio is 0.00639,205, is the fraction of the time region unit that is effective outside unit distance. It is therefore the unit of secondary mass applicable to the basic 2-dimensional rotation of the atom or particle. The unit of inertial mass is 1 such secondary unit plus 1 unit of primary mass, or a total of 1.00639,205. An analysis of the secondary mass relations enables us to compute the mass of each of the subatomic particles, a magnitude that is of interest not only as one more item of information about the physical universe, but also because of the light that it throws on the structure of the individual particle. Here we must take into account not only the 2-dimensional component of the secondary mass, the magnetic component, as we will call it, following our usual terminology, but also the other components that may be involved in the secondary mass. One of these is the component due to the electric rotation, if any. Inasmuch as this electric rotation, the rotation in the 3rd dimension, is not an independent motion, but a reverse rotation of the pre-existing 2-dimensional rotating system or systems, it adds neither primary mass nor the magnetic unit that is the principal component of the secondary mass. It contributes only the mass equivalent of a unit of 1-dimensional rotation. In this case, the 1/9 factor representing the possible positions of the basic photon applies directly against the basic 1/128 relation. We then have for the unit of electric mass 1/9 times 1/128, which equals 0.000868606. Now he's using the same factors that he used to calculate the interregional ratio, but with the interregional ratio, he uses that 1/156, and then he multiplies that by 9/11. Here, he's taking the 9/11 basically being 1/1 plus 2/9. Here, he's taking that 1/9 or that ninth, and he's having to multiply it by this 128. And he does that, I believe it's because we're not dealing with one of the two-dimensional rotating systems. We're dealing with just one because it's a subatom. And we multiply them together instead of basically adding them because they're independent, I believe. In this case, the 1/9 factor representing the possible positions of the photon applies directly against the basic 1/128 relation, whereas when you're calculating the interregional ratio, you're adding them. Anyway, this value applies specifically where the motion around the electric axis is a rotation of a two-dimensional displacement distributed over all three dimensions, as in a double rotating system. Where only one two-dimensional rotation is involved, such as the subatoms, the electric mass is 2/3 of the full unit, or 0.0005787, which is 2/3 of that earlier number, the 0.0086806. When two of the two-dimensional rotations, 4 dimensions in all, are consolidated to form a double rotating system, 3 dimensions, the two 0.0005787 mass units become one 0.000866806 unit. Another secondary mass component that may be present is the mass due to an electric charge. Like all other phenomena in a universe of motion, a charge is a motion, an additional motion of the atom or particle. We are not ready to discuss charges in detail at this stage of the presentation, so for the present we will merely note that on the basis of the restrictions on combinations of motions defined in Chapter 9, the charge as a motion of the rotating particle or atom must have a displacement opposite to that of the rotation in order to be stable. This means that the motion that constitutes the charge is on the far side of another regional boundary, another unit level, and it is subject to two successive interregional ratios or interregional transmission factors. The relation between the time region and the third region in which the motion of the charge takes place is similar to that between the time region and the region outside unit space. The interregional ratio is the same, except that because the electric charge is one-dimensional, the factor 1 plus 1/9 has to be substituted for the factor 1 plus 2/9 that appears in the interregional ratio previously calculated. This makes the interregional ratio applicable to the relation with the third region. 128 times 10/9 equals 142.2222. The mass unit of charge is the reciprocal of the product of the two interregional ratios. 156.4444 and 142.2222, and amounts to 0.00004494. The charge applicable to electrons and positrons deviates from this normal value because these particles have effective rotations in only one dimension, leaving the other two dimensions open. In some way, the exact nature of which is not yet clear, the motion of the charge is able to take place in these two dimensions of the time region instead of in the normal manner. Since this is on the opposite side of the unit boundary, the direction of the effect is reversed, making the mass increment due to the charge negative, as well as reducing its magnitude by 1/3. The effective mass of a charge applied to an electron or positron is therefore 2/3, negative 2/3, times 0.00004494 equals negative 0.00002996, 2/3 of that first number. We may now apply the calculated values of the several mass components as given in the foregoing paragraphs to a determination of the masses of the subatomic particles described in Chapter 11. For convenience, these values will be recapitulated as follows. Okay, so he's going to go over that, and we will go over that tomorrow when we resume. But basically, in this episode, he basically derived the mass units for all of the subatomic particles, and he's going to use all those various numbers to apply them to these various particles. So we'll be doing that tomorrow. Otherwise, have a great day, and thanks for tuning in.